Hi, my name is Martin Uhrin. I'm a scientist at FFL in Lausanne, Switzerland. And if you're watching this, hopefully you've seen the other two videos, parts one and two, introducing e3nn, a lot of the mathematical concepts needed to understand what e3nn really does and really what gives it its advantage. So what this tutorial is really all about is gently bringing us into the world of e3nn and actually using it. So in this case, we want to be using it to create a set of invariants that might describe an atomic system. And we'll play around a little bit with those invariants and see what kind of cool things we can do once we have a tool like e3nn. And also, especially through the hands-on part, you'll see how the fact that we have gradients that propagate all the way through gives us an extremely powerful tool with which we can play and learn a lot, but also do very important things that are useful for our scientific research. Okay, so the picture that I have here on this introductory slide is really showing what this is all about. So imagine I start with some kind of atomic system. I've got some atoms in Cartesian coordinates, and they have some atomic species. And I want to go somehow from there to a point where I have a fingerprint vector, so just a list of numbers that represents my original atomic configuration. So why would I want to do this? Well, many of you have probably seen and maybe are even expert in, for example, machine learning interaction potentials. So this is a case where you would be taking in your atomic system, your atomic configuration, and you'd be trying to learn the energy landscape. So what the energy is a function of varying the coordinates of the atoms and maybe even their species. So a typical neural network setup that might be used for this is to partition the energy into atom-centered parts, sort of like little blocks to make up your structure with a cutoff sphere around each atom, and you'd predict the local energy contribution for that collection of atoms within that sphere. Do this for all of the atoms in your system and sum the whole thing up to get the full energy. Of course, because of these gradients that propagate all the way through, you can also calculate the forces, which you usually need and help a lot with training. So that's just one example, but of course, energy, you can substitute that with whatever property you want, but as a function of the coordinates of your atoms and their species. So one might ask, okay, so what properties do we want from our phi, this input? So this is a vector that is an input to our neural network. And what are the things that we would like, the properties that we would like this object to have? For sure, we want certain invariances. So if we change the atom labels, instead of calling, one atom, saying this is atom number one, this is number two, swap them around, we for sure don't want the energy to change. If we globally translate the whole molecule, we don't want the energy to change. We know that the physical laws of data symmetry, so we want that to be baked into the inputs that we pass to the neural network. We want that if we rotate globally this molecule, the energy doesn't change. And then there are sort of other criteria that are niceties to have. They're not intrinsic properties of the necessarily symmetry properties of the energy, for example, but they are things that we need if we want to learn a smooth property like the energy. So we want smoothness, and of course we want completeness, by which I mean that all possible atomic configurations that are different should map to different fingerprint vectors that we then pass up to our neural network. And the reason we might want to do all of this is if we can create a fingerprint vector like this, then we can use any regression scheme we like. We can use a neural network, but we can equally use linear regression, kernel methods. We can do all sorts of learning on this, and it's a very convenient way to work with our atomic configuration. Now, of course, one could use e3nn directly, and then it has full knowledge about our atomic system, and we don't need to calculate invariance immediately. But this is a very convenient way that's historically been used a lot to create these kind of potentials and predict many other properties. So in this talk, I'll show you how we do that with e3nn and some of the nice things that we learn along the way. Okay, so let me just rerun the cell. Let's say we have this atomic configuration. So I've just taken an atom that I've created, a molecule that I've created, a urea molecule in this case, no, sorry, not urine, a molecule that we created using the ASE. toolkit. And I'm just going to use this as an example. So I bring it up initially, and you'll see a lot of examples like this, where what I'm showing is basically an array of numbers, and I'll change certain things about those numbers. So in this case, I'm showing you the positions, the Cartesian positions of the atoms in that molecule. And as I tweak this slider, what I do is I rotate the molecule globally, and you can see that in the printout of the XYZ coordinates, and I'm just rotating about the X here. So of course, our numbers change, and therefore so does the visualization. Now, if we translate, as we expect, the numbers change as well. Here I'm only translating the X coordinate of the whole molecule, so I'm moving along X, and we can see that getting brighter red or brighter blue. And we can, of course, permute the atom labels. So I'm just going to take one atom and change it with another one in the structure. So, of course, this description would not be suitable for Bayesian neural network because all of these symmetries that we know the physical laws obey are in no way respected by this representation. So how can we fix this? Well, we can start to do things that might seem very obvious to us initially. For example, for permutation, if we just sum the coordinates along X, along Y, along Z, then of course that sum doesn't change if we change the order. It's always going to be the same. So now you see as I swap the first atom with the other atoms in the structure, our visualization doesn't change, but of course we are still sensitive to rotations, global rotations and global translations. So next, let's deal with translation. So one thing we might think to do is, okay, let's just center our whole molecule and just subtract the center of mass. So it's always sitting at a particular point in space that we've arbitrarily defined. And of course, if we do that, then if we translate the whole thing, it doesn't matter because then we just end up subtracting off the center of mass and we get back the same representation. But of course, we've still got sensitivity to permutation and rotation. And next, let's deal with rotation. So the thing we might do is to say, okay, well, we know that if we square these vectors, we do the dot products with themselves. That is a quantity that doesn't vary. So the length of the vector or the length squared is going to be the same no matter how we rotated this molecule. So if we do that, we indeed see that despite the fact that the Cartesian coordinates are changing, the visualization is the same. However, of course, we still have the sensitivity to the other two. So we can think, okay, well, let's just combine these all. Let's put it all together. Let's center our molecule, calculate these squares of the vectors, and let's sum everything up. Great. So we've got a representation that clearly satisfies all our invariances, and it's just a single number. So clearly that is not a complete representation. There are many different molecules that can map onto this single number. So we need to do a bit more work to get to that point that we want to get to. Okay, so because you're already familiar with e3nn, you'll know that we're dealing with the spherical harmonic basis, and we're dealing with this because it is the basis of the irreducible representations of the rotation group, SO3. So if we have that basis, it's an orthogonal basis, so we can not only expand any arbitrary function f, or at least any function in Hilbert space, f in that basis, but we can also reconstruct that function. So if we've got the expansion coefficients we've calculated here, then we can perform synthesis and reconstruct an approximation to our original function. So that's looking like a good start. So to visualize this a little bit, what I've done here is I've just created points on the sphere, just uniformly created a series of points that I'm going to use to then expand in this spherical harmonic basis, which will give us a feeling for what this thing is. So here I'm just plotting the x, y, and z coordinates separately, and we see the color scale is giving us the magnitude of each part of this point set. Now, we can, if we want to get back to the kind of pictures that we often see on Wikipedia or in textbooks of spherical harmonics, the way that's done is that we deform these spheres such that the radius is equal to the absolute value of that quantity. So if I just apply that to all these points that we've created here, this is what we get, and you'll probably recognize those as the L equals 1 spherical harmonics. So let's compute the L equals 2. So what I'm doing here is just doing an element-wise tensor product and on those Cartesian coordinates that I have. And this brings us up to the L equals 2 spherical harmonics, which you'll hopefully recognize. And we can play this game, keep going up. So here I'm just doing the same thing, but going up to L equals 3. And I'll stop there, but you'll see that basically the function that we want to represent on the sphere, we can of course expand in this basis. And this just gives you an idea of what the functions look like that we're actually expanding our arbitrary function f in terms of. Okay, so let's go back to our molecule, do this expansion. So you can see here in e3nn what we're doing is taking the spherical tensor and we're using this helper function, sum of Dirac's. So what that does is just treats the positions of the atoms in the molecule as Dirac delta distributions in space, and then expands that in the spherical harmonic basis. In this case, I've said, please expand it up to L equals 4. Now, if I visualize the resulting tensor, of course, this is something that changes with rotations, translations, and permutations. We're not there yet, but we have a representation that's much easier to use to get to the point where we want to get to, which is, of course, a set of invariants to these symmetries. So to give you a little bit of a feeling of how the mathematics behind this works, it's useful to look at the actual rotation matrices that get applied on the individual subspaces formed by the different L's if we are to do a rotation. So as you maybe remember from Mario's talk, the advantage of working in this irreducible basis is that it partitions our space, our vector space, into parts that transform as L equals 0, L equals 1, L equals 2, and they don't mix between the different L's. We can see this here. As I change the angle of rotation, you can see that these blocks, these subspaces, change, but there's no interaction between them. Now, what you might have seen is that as I do this, the top left part, this little guy doesn't change. And that's precisely because this is the L equals 0 part. L equals 0 spherical harmonics is just a sphere. So of course, if we rotate a sphere, it's not going to change its value. So this is exactly an invariant that we want. The rest of the parts of this matrix do change. So we can't use those to get scalars from. But this top left L equals 0 part is a rotation invariant. So we found one rotation invariant, but clearly we need more. That's why we went down this route. Okay, so what we're going to do to create more invariants is we're going to start to do tensor products. So the first one is this guy here. But if we do a tensor product between two irreps at the same L, once we've done that tensor product, we can read off the L equals 0 part, so that upper left part of the matrix, and we get a new invariant. And we can keep going up. We can do further tensor products. And here we have additional degrees of freedom where we've got L1, L2. And so you can see we build up more and more invariants that give us more and more information about our original function that's been expanded in this spherical harmonic basis. So the way to do that in code is to use this reduced tensor product class, which amongst other things allows us to put in the permutational symmetry. So because we're going to do a tensor product of a tensor with itself, we want to tell the reduced tensor product, okay, these things have certain permutational symmetries, and I'm just doing the tensor product of the same thing with itself. So please take that into account and remove any redundant paths in this tensor product. So that's what I've specified here. It's basically saying that I can just swap any pair of indices in my tensor, and it's still the same thing. And so I define the bispectrum, which is effectively this tensor product of the same tensor 3 times. And now if I create a spherical tensor, same way as I did before, sum of Dirac deltas, and I calculate the bispectrum, as I rotate, we see that this thing is fully stable. The values don't change. So these are precisely the invariants that we're after that we can then feed into whatever regression scheme that we want, and we are confident that it's at least quite a rich description of our original function for us, of our original atomic environment. But is there something that the invariants tell us? I mean, is it just a set of numbers that we're to take as given? Or is there something to be learned from looking at the invariants, the values of the invariants themselves? Well, one example that I find quite useful is this one of, for example, if we take a tetrahedron. So I've just created 4 points in space, all atoms of the same species. And in this slide, I take a seesaw version of it. So you can see that 2 of the atoms have moved in and 2 have moved apart. And I can use this function to smoothly move from one configuration to the other. So that allows us to look at what happens to these invariants if we were to smoothly deform this tetrahedron into the seesaw shape. And as I do that here, so what I'm plotting going from left to right is exactly what the values are of these invariants, going from a perfect tetrahedron to that seesaw shape you saw above. So there are a number of things that we see. For one, there are invariants as we move from one to the other, the invariants all change smoothly. So this is hinting at the fact that these invariants do indeed have that property that we need, smoothness, so that there's no discontinuities, all the gradients are well defined. But on top of that, we also see a splitting. So here the values are 0, and when invariants are 0, that is usually a signature of symmetry in our system, and we know the tetrahedron is a highly symmetric shape. And as we move away from that perfectly symmetric shape, the signals actually split. So these things, from being indistinguishable, actually start to have distinct values that account for this asymmetry in the seesaw shape that I've created. So there's a real sort of beauty in this, that the invariants tell us something quite deep and profound about the geometry. It tells us about the symmetry of our objects. It's not just an arbitrary set of numbers that represent a rotational invariant fingerprint of the structure. Okay, so let's go back to our molecule. So this is the original molecule I created, and there's one part that I didn't go into. So what happens if we have 2 atoms that are behind each other radially? Now, as I said, the spherical harmonics are defined in the sphere, so there is no behind, it's just everything lies on the surface of the sphere. So if we want to represent something that can have any configuration in 3-dimensional space, then we need something in addition to our spherical harmonics. And that something takes the form of a radial basis or a set of radial functions. But basically their job is just to add in this information about how far away something is from the origin. So compared to before, you can see that all that's changed here is this integral now is going to integrate over the radial component. And I've put in a set of radial basis functions here that are feeling out what's going on as we vary the radius away from the origin. And just as before, we can of course reconstruct our original function, and we just need to include the radial basis. And we've kind of alluded to this already. What form should our function take? Well, it's just going to be a sum of Dirac delta distributions, and we can weight them to encode atomic species if we want. But this is the most convenient form to work in. There are others as well. We could put Gaussians on atomic size or others, but it doesn't really change the way that we calculate invariance. So what kind of a radial basis that can we use? What kind of functions can go into this RNL object? Well, there are many possible choices, and some are worse and some are better. But let's say if we want to be able to reconstruct an approximation to a function, the easiest ones to work with are those that are mutually orthogonal. So that allows us to exploit the formula we saw before for reconstruction, this one. And so what we do in e3nn is we take, for example, a series of functions like cosines, higher and higher harmonics of the cosines. And from this cosine basis, we perform a Gram-Schmidt orthogonalization, which basically says, okay, take this radial basis function and make the next one orthogonal to it, and the next one orthogonal to all the ones that came before, and so on and so forth. So after performing that procedure, what we end up with is a series of functions like this, with the k going out with the radius, and that are mutually orthogonal. And this is all done for us by calling this orthogonal radial functions class. So let's combine our radial functions with the spherical harmonics that we saw before. So what I'm going to do is use this different type of tensor, which understands how to combine the spherical harmonic parts, or the angular part, with the radial part. And then we've got a similar function here that we can use to create an actual signal. So effectively do this expansion in the spherical harmonic basis with our radials. And then we get a signal out, and that's just an ordinary tensor like the ones that we had before. And here what I'm plotting is I want to look at, okay, this molecule that we saw at the beginning, what does it look like through the eyes of this expansion? And what I want to do is plot this expansion as a function of increasing L max. So I'll go to the L equals 3, L equals 4, L equals 5 spherical harmonics. And this basically makes our basis set more and more complete. So as we add more spherical harmonics, we can pick up on finer details in the structure. And we see that here. So this is a very coarse-grained description of our molecules. If you remember from before, there should be some hydrogens down here that are basically gone completely. But as I add more and more spherical harmonics, the description gets more and more complete. And by the time I'm at L equals 6, I can actually see, I can make out these hydrogens fairly well, and quite a lot of detail in this reconstruction. And of course, the story with invariance is exactly the same one as before. So if I were to just calculate the signal that we saw there, you'll see that it's exactly the same story. If we rotate it, the entries of this tensor change. But if we perform the same, in this case I'm doing the power spectrum, so I'm only doing one tensor product and then reading out these L equals 0 parts, these invariants, we see that actually we get a fingerprint that doesn't change at all. So as I rotate the system, this is a fingerprint that now encodes all of that information about the three-dimensional positions of our atoms in our molecule, but it's invariant to rotations. Okay, so I've walked you through how to create these invariants from the spherical harmonic basis, and then how to add in a radial basis, get a fully three-dimensional description of a system, in our case, a series of atoms in space. And there's a tutorial that accompanies this. And the tutorial actually incorporates some of what I've been talking about here, and then goes a little bit further. So because we've got these a fully differentiable framework by virtue of using PyTorch, what we can do is actually play around with the gradients of the full function going from atoms to invariants. And we can even do things like take our invariants and then do a gradient descent from some atomic configuration to recreate the atomic configuration that corresponds to those invariants. And that's shown in the tutorial, and we play around a little bit with the kind of things that you can do once you've set up that kind of configuration. So have fun